So once again, this is the vector equation. This is the matrix equation. This is an augmented matrix. And up here we have the system of linear equations. And these are four ways of talking about the same thing. And why are we complicating things? Well, different points of view yield different techniques, and the more tools we have, the better. So some short forms, we'll have VE and ME for A and B there, and then system of linear equations. Now, these are all, as I said, logically equivalent. Let's write that down in a chain of logical equivalences. So we'll start with the SLE, the system of linear equations, is consistent. Okay, you'll recall that means that it has at least one solution. Now this is logically equivalent. We use this double-sided arrow to say logically equivalent, or sometimes translated as if and only if. Or if and only if, which equals, so if with two F's is a short form for if and only if. So the SLE is consistent if and only if, well, the vector equation has a solution. So we're going to think of that as, so the vector equation having a solution, what it says is that this vector 3, 6 is something times 1, 4 plus something times 2, 5, meaning that 3, 6 is a linear combination of 1, 4 and 2, 5. So write it down. Is a linear combination of 1, 4 and 2, 5. And finally, we can look at part B, the matrix equation, to get another point of view on this problem. So we can say AX equals B is consistent where we can specify A is 1, 2, 4, 5, B is 3, 6. Okay, so I guess I'd say three, maybe 3.5 different points of view here. And all three will be useful. Okay, with the SLE, we usually use the augmented matrix interchangeably. But the other 2 points of view will have their uses. Okay, all this discussion can be summarized in this theorem here. So please copy this into your notes. Beep, beep, boop, boop, beep, beep, boop, boop. So here we have AX equals B. This is the matrix equation. And this is the vector equation. Okay, to see the connection between those two, let's do this calculation one more time. So AX equals B. Now we're taking A and we're writing it in terms of its columns. So A would be like first column, second column, dot, dot, dot. How many columns we have? We have n columns. Now each column is a matrix, right? So we should put little arrows on top. Oops, each column is a vector. Sorry, each column is a vector, so put little arrows on top of those guys. So we have A times X is equal to, this is the vector X here. This is equal to B. So you got B1, B2, all down to BM. You don't necessarily need an M. I imagine so. Oh, whatever. So here's AX equals B. And what I'm trying to do here, if I've lost you, is I'm trying to connect the dots between this and this. So now I'm just going to perform this multiplication right here. We don't usually put a dot, but you put a dot for emphasis if you want. So this multiplication right here, when I do that, I take x1 and I put it in front of the column A1. Then I take x2 and I put it in front of the column A2. And then, well, I have some undetermined number of columns here. But the last one we'll say is A. Oopsie daisy. The last one is N. So xn, an. And this is equal to, well, we'll just write it as B here. There's no sense in writing that out.